I am Kyeong from Dongmin University, Korea. It's my great pleasure to welcome you all here today. The special session of Super Building R&D Center, shortly SuperTech. SuperTech was established in 2015 under the financial support of the Korean government to innovate world-best technology for super buildings. Today, we have 6 presentations. Each speaker will have a 20-minute presentation and 5-minute Q&A under the main theme of super tall building structural design and construction technology. At every 18 minutes for each speech, I'm gonna ring a bell for the proposal of the time management. Before moving to presentation, I would like you to join me in celebrating and bidding farewell to Professor Chung. He is the director of SuperTech Research Center. Earlier today, the retirement ceremony was held to honor his commitment and achievement as a professor at Dongmin University. As the last speaker of today's session, he is going to introduce Super Building R&D Center, and we are going to spend some time recognize his remarkable academic achievement. Let me introduce Professor Chung. Please give him a big hand. Okay, the first presentation is multi-mode system identification and control using an active sensing device for building structure by Professor Hyun.
Thank you for introducing me. I'm happy to be here as a first presenter. So, because I have been working with Professor Chung for about 15 years, I know him very well. I have conducted so many research projects with him. The first title of my presentation is Active and Hybrid Controls of Building Structures in the Wind and Earthquake Zones. I'm Sanarmin. I made this presentation with Professor Chung. I briefly made a few slides in addition because this is the first ceremony of retirement of Professor Chung. We are speaking about Professor Chung. There is one accident in Korea. Samsung department store collapsed 1995. The collapse is the largest disaster in peacetime in Korea. The normal building collapsed without any terror, any attack, and any bomb or any structural failure. It was the deadliest building collapse until the 9/11 attacks in New York City. Professor Chung was the investigator, the cause of the big building collapse. Paradoxically speaking, the collapse of this building was the cornerstone for structural safety in Korea. Based on this collapse, Professor Chung insisted that structural safety is the most critical factor in design of building structures. The collapse cause was the punching shear failure of the flat slab system. The column reduced below the required one. Surprisingly, an architect, without any consult from structural engineer, he decided the reduction of the column size or the loading of the design load and then column excavating for installing escalate and fire shield. Now I'm going to show you the project, several projects with him. The first one, high performance material. This slide shows the high tension steel reinforcement experiment. Based on this experiment result, this high strength steel reinforcement was used for Lateral World Tower. This is the tallest building in Korea and fifth tallest building in the world. And then we conducted so many research regarding the sizing engineering. It's the in-situ test of a 3-story building. Can you find Professor Chung? Professor Chung is attaching a strain gauge on the side of the column. He is very enthusiastic and energetic, especially in full-scale testing. Also, he developed the fragile cover of building structures. The Prestressed cover of the building structure was embedded in the control program of National Emergency Management. So now Korean government can estimate the earthquake damagement using by these Prestressed covers. Also, here I conducted the storm fiber modeling. This Korean traditional natural heritage. We model this storm fiber by using discrete model. Another and the most important projects were based on the structural control and monitoring. The first one, semi-electric control. The semi-electric control utilizes the magnetic electrical damper of the material converts from liquid to solid in milliseconds by simply inputting voltage signal. And then we developed active control first in Korea. We have some practical application by using this active mass damper. I'm going to show you this application in detail for my presentation. Another is a hybrid passive control. This damper can control both wind and earthquake loads. Another projects are for monitoring. The monitoring the building vibration accurately is most critical in modern society. So we are going to conduct project LED display, Tecma Training and Lateral Tower. First is the actual control. Before we start of this project, the Korea is the wasteland in actual control. All the products for actual control was imported from Japan. We first developed this prototype of active mass damper and applied to the 5-story steel structure. We verified the performance. The active damper can significantly reduce the structural response. We developed also control algorithms. After the success of this damper, the prototype of damper, we are looking for the practical application. Who is going to use our damper? Well, who is willing to use our damper without any practical application? In that time, abnormal vibration at a 39-story building structure was occurring. Mystery shaking empty solid building. The 39 technometer shared for about 10 minutes. No earthquake in the area. The building was rocking up and down, and I felt so dizzy that I almost vomited. All the residents evacuated for 3 days. Everyone, including us, every Korean was shocked. Because I think that this is due to the trauma from the collapse of the Samsung department store. Normal building may collapse in normal time. Korean people may have trauma about the building collapse. So the Professor Chung was the person in charge. Also, I took part in the research director. The objective is identify exact vibration source. There were 4 suspicious vibration sources. One is wind rock, the other is vibration of mechanical equipment. The third is exercising fitness center. The fourth is body theater. Chair vibration in body theater. The last is foundation settlement. Because many people reported that they felt the vibration in vertical direction. Everyone, including us, were worried about the building may settle down or collapse. But the wind speed at that day was so small, and the mechanical equipment operates all day, but the vibration accident only occurred in 10 minutes. So the building was mounted on rock site, so only 2 vibration sources are considered as vibration sources. The experience was conducted on the 40th. This is the 40th floor, and then the accelerator was installed at the office building. The vibration accident occurred at this office building. This slide shows the movement of the 40th. After start of the movie, the floor of the 40th vibrates significantly. But however, the office building does not move any response according to the 40th stars, and after the stars, there is no change of the vibration. Only the human-induced vibration can be observed. This room was not occupied by human. And then we constructed an analytical model. We could find the vertical model. The frequency of this vertical model has 2.7 Hertz. It's just small, 2.7 Hertz. So we could estimate that this building can be excited by human. I'm going to show the public rehearsal. This movement is on the 12th floor. Here is the acceleration and 38th floor. This is the general movement. It's called as taekwondo. It's a mixture of taekwondo or aerobic. In normal time, this does not cause any vibration amplification. However, people are stepping according to the frequency of the building structure. I think you should notice this amplification of the building structure, acceleration. This voice is from Professor Andrew. 해보 열심히.
앞에 걸 좀 열심히 하면 이런 템포가 되는데 지금 이런 템포는 벌써 집폭이 엄청나게 커진 거 보실 수 있죠. 그래서 이 템포를 맞추는 게 중요한데 당시의 템포가 그날 세봉 강사분이
The tempo of that day was tuned, accidentally tuned to the frequency of the structure.
해보는
Here is the measurement result. The 12th floor movement was not significantly different. The general excellence from to rhythmic stepping, just a little bit larger. However, the structural response was amplified by this movement. We measured the inherent damping by observing the free vibration after the excitation. The inherent damping was just 0.3%. It's too small. It just consists of steel box column. And then vertical movement does not cause any friction between cladding or other elements, so the friction or damping was so small. We made a TMB to control the vertical movement. This sample device acts as in vertical direction. It acts as a tuned mass damper. It's a blue part, and then the total part acts as play a lot of active mass damper. We are gonna develop this type of damper for controlling both in vertical direction and in horizontal direction. This is the process of the construction. Damper was successfully installed, and we conducted the experiment. Here is the steel plate, which can prevent the movement of the TMD. By installing the steel plate, we could reproduce the resonance phenomenon. Only 10 people can excite the building in global direction. Here, the red line is the resonance result. You can obtain the same result at that extent. After removing the steel plate, we could get the TMD impact. You should clearly see the structural response was reduced significantly. The damping increased from 0.3% to 2.7%. Also, we conducted a wind tunnel test. Although the vibration extent occurred in vertical direction, the owner of the building worried about another load may excite the building. The brand of the building was so damaged. The owner of the building could not buy sell this building to other person. He wanted the building has no vibration extent in any manner. So we conducted wind tunnel test. By conducting wind tunnel test, the building is not so tough stuff to the wind road. The surface clarity was so large. And then after we had two typhoons. One is 2011 and the other is 2012. We measured the structural response. Every person in that building felt discomfort during that typhoon. So we decided to the active mass damper in horizontal direction. But in order to reduce the 50% response reduction in horizontal direction, 120 ton TMB was required. However, the additional mass limit was limited to 80 ton. This is an existing building. It's not designed for damper installation. So we developed active mass damper by reducing the mass to a half level. Also, there is another limitation. The installation space was so small. And then because the stroke was very small. Small mass, small stroke is very hard condition for me. So we developed a stroke minimization control algorithm. Here is the algorithm. We could minimize the stroke. This pendulum symbolizes the building movement. Here is me. The active mass damper acts according to the structural movement. Can you see the wood? If this mass strike this wood, we will fall off, and then we fail. we design how large excite the building pendulum to an extreme level. This mess should not touch this wood. After installation of the active mass damper to a tachomat, we conducted a system ID. We could obtain the system identified result. You can see the identified or measured results were almost identical. System was accurately identified. After the installation of the damper, the first mode, second, and third mode damping ratio increased significantly. Based on the success of this active mass damper, we could obtain another practical application. It's in Chung airport control tower. We conducted performance test. We could estimate the scale of the active mass damper. It's very small. Here is the pendulum type structural model, which models the movements of the structure. The two dampers were installed in Chung Airport. An in-situ test was conducted. You can clearly see that damping increased significantly by installing damper. Also, in y direction, movement could be controlled. We are going to apply this active type damper to a practical project, which Chung City Tower and US Drama, Wangan Hanman Public Corporation. This is another project for passive control. The development of a multi-action hybrid damper for reducing wind and earthquake responses. This is an LRB, red rubber bearing, and this is friction. If the slippage of the friction test does not occur, this movement can be rigid. So before the slippage of the friction pad, only all deformation concentrates on the LRB. So for small deformation was not enough to excite large deformation. It's something like wind loads, only LRB dissipates structural energy. For large deformation induced by seismic load, after the slippage of the friction pad, only friction pad dissipates structural energy. So we developed this passive type control device for both controlling wind and earthquake load. Cyclic test was conducted. We could obtain the hysteretic curve using this damper. For small deformation, only LRB shows the hysteretic curve. For large deformation, it's something like a typical friction damper characteristics. We simulate the performance of the damper under wind loads. We generate wind load by using wind load spectrum. And then we could estimate the building response reduction ratio by using dust factor and equivalent damping ratio. Also, by installing the damper, the increase of the damping ratio was calculated. Also, we could estimate the wind load reduction factor. The crossing point was the estimation, just the estimation, the building reduction ratio. It's 0.596. Finally, we simulate the building response by using the generated wind load we could obtain the popular display reduction ratio. It's a 0.585. It's almost similar to estimated one. Also, we conducted the rear scale building structure using by 5-story structure by installing the damper at the first floor. The transformation was reduced significantly. Also, we simulated the damper performance for the seismic protection. We could obtain the estimated result for small deformation and for large deformation. It's a combination of two hysteresis. So full-scale one-story building experienced loss control. We could obtain the increase of the initial stiffness and then the hysteresis. For small deformation, when enlarging, the deformation increased. There was no movement in friction pad. After scraping of the friction pad, only friction pad increased the structural damping or displacement. Now I'm to a conclusion now. This is the summary of my presentation. Also, I would like to end my presentation with a special thanks to Professor Chung. I have conducted these all 3 projects with him, so I was happy, and I'm happy now. Thank you.
Comments from
Actually, thank you very much for your very informative presentation. I did active control.
Please introduce yourself.
Yes, of course. My name is Chung. I came from Qingdao University of Technology. Previously, I worked in Harbin Institute of Technology in China, and I did the Guangzhou Tower.
Guangzhou Tower?
Yes.
Yes,
that's my job. Yeah, I did a hybrid control system.
It's based on TMD and
AMD. Yes. And I can understand you have the passion in doing so many interesting things and works. And I have one question and one comment. So the question is, you mentioned about the space, the stroke limit, and the mass limit. And you use some specialized algorithms to fully utilize the active control, but maybe due to the time limitation, they didn't mention details about the algorithm. I want to know if you could elaborate a little bit on the algorithms you utilize for that project. That would be great.
It's just international patent. I made international patent on reducing the displacement, the active mass temper. I added the constant velocity term into in calculating the active force. Constant velocity does not cause any acceleration. So the damper force was not changed by adding the constant velocity. So it's not so simple, but that's all.
Yeah, but it works.
It works.
Yes.
It works. It worked very effectively. So we reduced the stroke about half level to general AMD.
Okay. And my comment is regarding the active control. This is the first one and then the second one, and probably there will be a few others ongoing on maybe in the future. I want to know your
Of course.
your thoughts in applications for active control, particularly in Korea.
Thank you.
Okay.
Okay, my name is Kyeong from Dongmin University, Korea. My title is Design and Implementation of 3-dimensional BIM system for structural detail design. The final system name is Build a Hall. Before my presentation, I appreciate to Professor Chung. Actually, I am working with him, and this research can be done under his support, and I really celebrate his retirement, and his excellent and exceptional academic achievement throughout his more than 30 years professor life. Thank you very much, Professor Chung. Okay. Okay, Builder Hub is automated 3D structural detail design and 5D construction management system specialized in reinforced concrete structure. The core technology of Builder Hub includes three-dimensional conversion from 2D drawings and 3D rebar auto tracing based on design code such as KBC, Korean Building Code, or ACI, British Code, and etc. And Builder Hub provides precise quantity estimation, including rebar, concrete, and formal. And it provides five-dimensional project data integration and schedule management. 5D means three-dimensional design information and schedule information, the first one, and the fifth one is cost information. Then Builder Hub also provides beam data exchanging function with the commercial BIM software such as Autodesk Revit or Tekla and etc. The first core technology of Builder Hub is auto-recognizing 2D drawings for generating 3D BIM model. Let's watch a movie, short movie. Okay. Builder Hub has read the 2D drawings, select beam layer from AutoCAD 2D drawings, and read this drawing and generate 3D object like beam. The next step is read this floor slab, read this, and you can see the slabs generated automatically by recognizing the 2D drawings. Throughout this process, you can finish basement structure and the tower structure. Using this function, the productivity for modeling, three-dimensional BIM modeling can be increased up to 300% comparing with the commercial BIM software. And the next function of Builder Hub is generating 2D drawing error report and crowd mark during recognizing 2D drawings. During recognizing 2D drawings, Builder Hub produce error report like this and export to Excel and add the crowd mark to the original 2D drawings. this report and drawings will be sent back to the design office and request redesign and fix the errors. And throughout this process, we can minimize the reconstruction possibility in the face of actual construction phase. Okay? The next function is extract rebar sharp drawings. Usually it is more than 1,000 drawings, and it takes more than several months to finish such a sharp drawing for rebar work. But after finishing 3D BIM model, the rebar sharp drawings can be extracted automatically according to the construction phase in construction site. So, in addition, the drawing process, more than 1,000 drawings, is very time-consuming and very tedious and very error-prone work. But by this automatic extraction from 3D BIM model, we can reduce the possibility of drawing errors to 1/10 comparing to the traditional process. I'm sorry. So I completed. This is a process to produce the three-dimensional rebar bar bending schedule automatically, setting the design options and the rebar detail shape and the length, and including splice and anchorage can be generated automatically. Based on the three-dimensional model, we can get the very precise structural quantity by just one click, including rebar and concrete and formwork. It is very difficult to take out the precise quantity for rebar because it is very difficult and complex to include the splice design and anchorage design for rebar detail. It takes it is very difficult, and usually the error ratio for the rebar quantity is reached to 10%. But by automatic calculation of rebar quantity from three-dimensional model, we can reduce the error ratio of rebar quantity up to 1%. That's a very I explained this process just before I completed. This process is to produce the rebar sharp drawing, 2D sharp drawings to construct rebar work inside. Read this part and create, generate rebar sharp drawings and bar bending schedule to send to Riva factory. Build-up has a function to generate wage activities. Function to generate wage activity and export these information to the commercial schedule management software such as Microsoft Project or Primavera. After that, field engineer can arrange the actual schedule according to the site management. Then build hub get back the schedule information again, and construction schedule management or cost management can be done according to the construction schedule. The next core technology is excellent interoperability with other commercial tools. This example will illustrate how to build how export the structural model to Revit, including Riva information like this. This model shows build hub model, and this model shows the Revit model. This slide shows Riva process based on build hub. After 2D CAD drawings, design drawing or 3D BIM model is given to the build hub users. The build hub then produced 5-dimensional structural information, including 3D frame shapes and Riva placement and Riva concrete and formal quantity and construction schedule. These information can be used by main contractor for the schedule and estimation review, and the 2D shop drawings can be extracted automatically from this model, and the Riva schedule will be sent to manufacturing plant to make actual Riva shapes, and the field office review the 2D shop drawings extracted from the model and change the small changes, and the actual construction work can be done based on the placing drawing and cut and bent Riva from Riva factories. From now, this build hub is used widely in Korea by main contractors such as Daewoo, MGS, and recently Korea Land and Housing Corporation is a national corporation, includes this software as a design standard to build apartment in Korea. From now, I will show you some practice effect of build hub throughout actual site practice. This slide shows discrepancy and missing information in 2D drawings, which are automatically detected throughout the recognizing the drawings. The same one, but different. The same one has different information between the drawings, and these kinds of error information is are listed like this and exported to Excel spreadsheet or any other software such as Naviswork is a very famous software to simulate a construction site produced by Autodesk. And this three-dimensional BIM model can be used as a communication medium for all project participants like this. So we can find interference check and some very complex parts like this. And And Build Hub shows the material distribution throughout buildings. In this case, most of the members has 13 diameter rebars, but this member has 16 diameter rebar. This make some problem in construction phase. We can find this kind of mismatch using Build Hub model. We can use the Build Hub model as a value engineering tools. We can try several kinds of rebar detail, like this one or this one. Just to select after make a model and this alternative and this alternative, we can compare the total amount by just roughly, because Build Hub produce accurate quantity and automatically. And using this automatic quantity calculation function, we can compare many kinds of alternatives and many kinds of detail, and we can choose the best one. Okay. So this slide shows the accurate quantity information to export spreadsheet like Excel. And interoperability with the commercial authoring tools like Naviswork or Revit. Okay, so nowadays, Build Hub is widely used in Korea, construction company and estimation company, and many such companies review and check the productivity and the accuracy of Build Hub product. Throughout this review process, we can find that the productivity to build a three-dimensional BIM model can be increased to the 3 times comparing to 3D commercial BIM tools such as Revit. And and the total cost of structure can be reduced by 5 to 10% by automated and efficient design and management. The quality and real-time feedback like this. Okay, so thank you very much. Any question or comment? Question? Yeah.
One question. How much does this builder have this software cost?
So where are you from?
China.
China? Okay. So I have a partner in China. The partner company now are using this software, and they are selling in the whole the Chinese construction market. And but 20,000 US dollar. Yeah. But you think that it is a little bit expensive, but I think we found that usually one construction site can reduce the total construction budget up to 3 or 400,000 US dollar by applying this software to do accurate work for river and formal. So many Korean construction companies are satisfied by applying this technology to actual site. Yeah.
This is a pre-construction and during the construction. Post-construction, you can also prepare the as-built drawings using the software.
Yeah. At the pre-construction stage, usually this software is used to take out the total cost and total quantity, but at the stage of actual construction phase, this software usually used for the produce shop drawing and construction detail drawings. Yeah. So after we make this model one time, the digital information can be used to every step.
In addition to the rebars, you have several other materials. You can incorporate all of that and use that for the maintenance of the structure later.
Actually, we have only function for structure, including especially specialized in reinforced concrete structure. But this model is the starting point for the 3-dimensional model because we can do any other following activity such as MEP or architectural finishing can be done after structural model. So many construction companies use this software at the starting point of 3-dimensional model, and export this model to commercial BIM software such as Revit, and they usually do MEP model and architectural model with other software. Okay, thank you very much. And the next presentation is
Okay, my name is Dongmin and I'm a PhD student in Korea University. Actually, the subject is a little bit different from that I suggested earlier. So today, we're gonna talk about advanced lifting technologies and formwork systems for turbine construction. So I'm honored to be with you today at this great ceremony, retirement ceremony, and it is a special session. Let me start it. Yes. Yeah, okay. Thank you. Okay, the contents are as below. The first of all, I would like to talk about the trend of tour building and the characteristics of tour building construction. So the graph is the cumulative number of tour building over 200 meters during from 1920 to 2015. So the graph is rapidly increased for within a century. So the tour building market was expected to continue growing until 2017, and 1970 tour buildings over 200 meters constructed in 2014. And the important thing is the average height have been increased about 100 meters for the last 10 years. So the graph below shows that the average height of tallest 50 buildings in the world. So it's increased very slow motions. So the first trend is the super tall trend. So these buildings are all higher than 500 meters, and the Hyun Tower, the Saudi Arabia, is almost 1 kilometers. And the second trend is regular shape trend. So these buildings are tapered and twisted and tilted. So why is it important when we do research or making a building? The existing tall buildings have repetitive typical floors, so we can use modular formworks for reusing the slab formwork. And also we can use vertical forms such as ACS, GCS, RCS until to the top floors. And also they have straight exterior walls, so mast means the lift mast, can be installed perpendicular to the exterior walls, and the maximum installation height of lift car is 200 to 300 meters. But in this latest tour buildings, according to the high-rise and irregular shape trend, the typical floors changing continuously every 4 hours. So we have to install wood form in the irregular sections, and additional extra forms to be installed according to the change of shape of exterior walls. And also because of the irregular exterior walls, we have to use temporary facilities to maintain horizontal level between lift and building. And also we have a limitation on installation of existing construction equipment. So the constructability is decreased and the cost also increased, since additional materials and labors must be delivered with existing systems. And the third trend is green. The building is all river towers and the shape is looks weird, but there is an air turbine inside of the building, so the zero energy building can generate the energy inside of the building. So actually the tall building is characterized by their high energy consumption compared to another building types. Since they rely intensively on their HVAC systems due to their extreme weather conditions associated with increase in height. But also they have an opportunity for energy savings in recent years, maybe it has been noticed that many software, something like parametric modeling or 3D visualization tools, so we can design energy-saving buildings or tall buildings. Even in Korea, the nuclear power plant is diminishing as years goes on, so in the future, maybe the zero energy tall buildings will be a significant research part in the future, I think. In the chapter 2, I'd like to talk about the lifting technologies for tall buildings. So how can we respond to the trend, irregularities and supporter trend and wind. So the first one is irregularity tall building lift, and the second one is lift power system, and the third one is green lift technology. There is a previous lift mast, and as you can see in the picture, the lift is stand and move vertically near the buildings, but in the irregular shaped buildings, there is a gap between lift mast and the building, so we have to install the temporary scaffold and temporary towers and connecting passages. So because of that, the efficiency can be lowered, caused by an unnecessary transfer and the increased distance between lifts and buildings. Also, the operational cost could be increased and the construction time will be increased due to the additional material installation. So, firstly, we developed inclined construction hoist. So, one of our purpose was they should keep the horizontal level of the lift in response to irregularity buildings. So, we are setting the 13 masts on the exterior walls by installing spacer between the existing masts. And to keep the horizontal level of cage, we used 4 hydraulic jack in the 13 hinge with sensors. And the maximum allowable 13 level was customized 6 degrees for maximum height, 600 meters. So this picture is inclined hoist, so you can see the inclined points in the mast. And in the operating cost aspect, the technology reduced approximately to 26% of material cost of temporary platform. And in the transportation time, about 28.8% of efficiency is increased by reducing transfer and horizontal movement. The next one is lift power relay system. So the power cable system has many problems on twists and breaking of the cable. So even high tension cable have a possibility with cutting problem in case of over 300 meters of buildings. So once the building, the cable is broken up, if there is a breaking, then it causes very big disadvantages that cost damages. So we have to solve that problem. The lift power supply system is a method of supplying power by contacting with conductor housing face to mast. So the most significant advantage of this technology is we can apply to any buildings higher than 550 meters. And it also doesn't require any cable system, so we can get rid of any accidents by cable. This is a technical effect, so there is ABCD site, and this site is applied power relay systems. And when we see the failure time and maintenance time over operating times, it's only 0.14%, and it's groundbreaking difference between compared to previous power cable applied site. And the next one is green lift technology. This diagram shows that how the lift generates energy. So the motor energy regenerated, and the inverter storing energy, and the regenerator convert the energy to use the energy in the So the recent high-rise trend in turbo building construction provides a more advantageous condition for the green lift since the regenerated energy is proportional to the height of the building. So in the technical effects, almost 55% of energy is regenerated. It means 1 kg reduce 2.3 million won a year. And the cost of this equipment is almost 5 million won, Korean won. So maybe break-even point is 2.2 years approximately. The third one is formwork system for turbo buildings. So how can we respond to the facades and the irregular floors? So we approached with these three topics: vertical form, concrete facade, and horizontal form, concrete floor, and building technology for formwork. A previous vertical form for turbo building has three components: profile, grounding, shoe, and anchors. But it is hard to apply the vertical forms to an inclined structure since the anchor and shoe are fixed. Profile is limited to the vertical movement. So this technology could be applied to any regular shaped buildings, but there is limitations when we apply this technology to irregularly shaped buildings. So we newly developed an anchor extension unit. So the anchor can cope with the vertical distance using extension unit, so it could be applied to the setback area. And also we improved the profile angle. So the profile angle can be adjusted about ±7 degrees vertically. So it can be applied to steadily inclined area. Also the shoe is also improved to be able to rotate cope with this twisted structure. These technologies are widely applied to practically in construction site. The next one is the horizontal form, concrete floor. So this is a sky deck and this is a brick table. So this kind of modularized formwork are widely used in turbo building construction to increase their productivity of formwork. But the formwork productivity is decreased since much cost and labors are required to install the conventional non-modular form to the in the irregular shaped area. So that's why we developed horizontal form. That name is the flexible table form. So the flexible shape by adjusting the length of adjusting beams. This is the adjusting beams. So they can cope with any kinds of floor region, even around columns and doors. So we can minimize non-modular form coverage area. This is a technical effect of the flexible table form. So previously, the modular form table form covered only approximately 80%. The black shaded area is conventional form, so the less the better. But in the flexible table form, we can cover 95% of area by using modular form. There's huge difference. And the third, so last technology is lifting technology for formwork. So previously, the form lifting method is proceeded by these 4 steps. The first, the strip and shift the form unit with the trolley and roll and pipe the unit with the PC, the top crane, and lift the unit and install the unit while supported by the PC. But it was time-consuming work and top crane became very overloaded. So that's why we developed automated lifting system. This ALS is integrated with construction hoist and use the hoist and mast together. So by using this technology, we can improve the productivity and safety of formwork lifting because we don't have to use any top cranes or any other temporary facilities. This is a simulation research of these 2 methods, by top crane methods and automated lifting system. So as a research, we verified almost 42% of improvements in productivity. And also 36% of top-line operating time was reduced. So in the providing construction, the top-line do something, many different work tasks. So if we can reduce the operating time of crane, then the top-line do something other more important organs, then we can reduce the construction time or construction cost more efficiently. That's a conclusion. So it's true. So in the promising future trend, high-rise and irregular shape trend continues, considering the landmark effect of turbulence and an advanced lifting technology that reduce unnecessary movements and transfer has widely been developed in the future. In the future, a technology which improves lifting efficiency will be researched. And also, I think a software and engineering technology for the system homework method will be needed in the future to manage and to operate the former method more efficiently. Thank you.
Any comments and questions? We made some several minutes. We are going to the next speaker. Thank you very much.
Thank you.
Good afternoon. My name is TaeSung from Kyeong University. The title of my presentation is Lateral Force Resting Behavior and Shear Design of Distributed Backwards in Buildings. This is the background. In high-rise buildings, outrigger and belt structures are usually used to rest against huge lateral forces due to wind. As you can see here, if this kind of massive outrigger structures are used in conjunction with forwards, there may be some constraints on architectural design because these outriggers disturb the space. So, and at the same time, as you can see here, conventional outrigger and belt structures are very massive. So, as you can see in this photo, variations in building facades and space planning can be significantly limited by the presence of outrigger and belt structures. There is another difficulties of conventional outrigger and belt structures in structural detailing and construction. As you know, conventional outrigger and belt structures should carry huge significant forces. It means that we have to make such a massive outrigger and belt structures with steel or steel concrete materials rather than concrete. However, as you can see here, core walls are usually constructed with concrete. It means that in the construction of this kind of tall buildings, there will be interference between two different construction methods, such as core wall concrete construction and steel outrigger construction. So in this case, such a mixed use of different construction methods can cause huge construction delay or cost increase. At the same time, we have to think about the structural detailing and the connection between the concrete core and steel outriggers. As you can see, the detailing is very complicated because there is a huge force transfer in this connection. In this study, I'm trying to propose a new an alternative structural system for buildings. I made it distributed backwards as a virtual, which acts like virtual levers. In order to understand the basic concept of the proposed distributed backward system, we have to take a look at the basic concept of virtual outlet systems, which is basically proposed by Chung in 1998. You can see here building animation, 76-story high-rise building, and you can see two different structural systems here. As you can see here, this structural system is composed of a core system at the center, and there is another outrigger trusses connecting the core and perimeter counters. There is another structural system on the right. There is a core system at the center of the plan, and there is another belt trusses around the perimeter of the plan. And these systems are totally different systems, but according to the analysis done by May, the structural efficiency or structural resistance of these two structural systems are almost the same. It means that even in the case we use belt structures without outriggers, like this system can provide sufficient structural performance for the lateral forces. Chung later named it virtual outrigger effects. In this study, I went further the concept. Actually, first, in the previous slides, I said that there is a interference between two different construction methods in these high-rise buildings. So I replaced the conventional steel belt with concrete belts, concrete belt trusses with concrete belt walls. Basically, the basic behavior of this concrete belt wall is the same as that of the steel belt trusses. So, as presented here, we can expect that by using the concrete belt walls, as you can see here, we expect some structural advantages. And at first, I thought that I have to place the belt walls at a couple of floors, as you can see here, in the middle stories and top floors. But if this kind of concentrated belt walls work well, why not distribute these belt walls around the perimeter of the plan and along the building height? So this is my new alternative. This is my alternative system, high-rise structural system for high-rise buildings. I made it distributed belt walls, as you can see here. From this slide, I'm going to show you the structural performance of the proposed belt walls as virtual outriggers. For this, I conducted a parametric study using -10, and this slide shows the building, prototype building, a third-story building, and you can see a core at the center of the plan, and there are 24 columns around the perimeter. And this is, I consider only our x-axis wind forces. As you can see here, this is the profile of the story wind forces. In this analysis, I compared the behavior, I investigated the behavior of concentrated belt walls which acts as virtual outriggers. You can see 4 different structural systems for tall building. The first one is conventional core outrigger belt system, and this third system is the proposed concentrated belt system. There is a core at the center, and at the perimeter you can see 2 belt walls surrounding the core. This is the results of the analysis. In this slide, the horizontal axis is the lateral displacement of each story, and the vertical axis is the floor number. Definitely, the most efficient system, structural system, was conventional core outrigger belt system. However, what is interesting, what is surprising here is that even though I did not use outrigger directly connecting the core and the belt outside the belt walls, the lateral displacement of this building was not that large. Actually, the difference between the lateral displacement and the roof was very small. It means that this kind of system is very effective in reducing lateral displacements because these belt walls act as virtual outriggers, even though there is no actual outriggers were not provided. This is the second parametric study. In this slide, I'm going to show you the structural performance of the distributed belt walls. You can see 5 different structural systems, and in each system, you can see different belt wall configurations at the perimeter. This is the results of the analysis. This result shows that no matter where the belt walls are placed, this kind of distributed belt wall system was very effective in reducing lateral displacements. And in this slide, I'm going to talk about the basic lateral force resting mechanism of the proposed belt wall systems as virtual outriggers. First, I'm going to talk about the concentrated belt walls. On your right, you can see the conventional high-rise buildings. In this building, there is only a core wall to rest the lateral forces. Take a look at these column actual forces. At the corner, you can see very large column forces. Along the side, the column forces are significantly reduced. It means that in this system, there will be a significant shear lag. That means this system is not effective to rest the lateral forces. On the other hand, on the left, you can see this is the proposed concentrated lateral systems. If you look into the column forces around the perimeter, actually the variation between the column forces was significantly reduced, and the actual and the overall magnitude of column actual loads was significantly increased. This clearly shows that the proposed concentrated belt walls are very effective in resting lateral forces, and these belt walls truly share the lateral force resistance with these core walls, even though these belt walls were not completely connected to the core. The same phenomenon can be found in the system of distributed belt walls. As you can see in this diagram, this is a core, and these frames is the perimeter frames. And as you can see, if this core deformed laterally, since the lateral storage shear stiffness is very big because this is empty. So in this period, we cannot expect any significant contribution of these perimeter columns to the lateral stiffness. However, in this system, if there are belt walls between vertical columns, and this core wall deformed laterally like this, and we easily understand from this diagram that there will be a downward force in this column. On the other hand, there is an uplifting force in this column. It means, as you can see here, there will be a significant shear force acting vertically on these belt walls, and these belt wall forces is definitely the counterpart force of the column axial force induced by this mechanism. And these belt wall forces were transferred through the top and bottom floors from this core. This slide shows the lateral force resting mechanism of the concentrated belt wall systems. The basic mechanism is the same as that of the distributed belt wall system. So far, I have shown that the proposed concentrated or distributed belt wall systems are very effective in resting lateral forces. And from this, I'm going to talk about how to design these kind of belt walls. As I said in the previous slide, these belt walls will be subjected to huge shear forces, and this force is the same. This force is pure shear. In this case, the belt wall will be subjected to diagonal shear cracking. You may think that if this wall is reinforced by horizontal and vertical reinforcing parts, this wall, the resistance against shear cracking will be very high, but that's not true. Actually, we have to think about the magnitude of these shear forces, and these shear forces is beyond our expectation, I think. And I propose the new reinforcement method for the belt walls. As you can see here, I'm going to use prestressed belt walls for this system. By prestressing the strengths placed horizontally and vertically, I think the resistance of concrete against shear cracking can be significantly increased. For the design of such a prestressed belt walls, we have to think about two issues first. The first issue is that the load condition of these belt walls. Actually, this belt wall, as you can see, this belt wall is subject to shear. However, when we think about shear design over reinforced concrete member, these equations are very familiar with us. But actually, these equations for the wall subjected to bending moment and shear, so we cannot use these equations for the design of belt wall. So we have to develop a different strength equations for the belt walls. And second, we have to think about the mismatch of two different material strengths. Actually, if we use pre-stressing strengths, the yield strength of pre-stressing strength is often is more than 1860 megapascals. However, the compressive strength of the concrete used for the belt wall is usually less than 50 megapascals. It means that, as you can see here, as you can see in this diagram, the yield strain of the pre-stressing strength is usually 4 or 5 times greater than concrete failure strain. So in this case, it is very easy to occur this kind of concrete failure. So in order to avoid such brittle concrete failure before the yielding of pre-stressing strength, we need a more advanced design methods, that means we need to develop a strain-based design method for the prestressed battery walls. In this study, I developed two strength equations for the prestressed battery walls by using the compression field theory. And this slide shows the biaxial stresses of concrete and the uniaxial stresses of strands. Actually, the basic concept and the detailed formulation is very difficult, so I'm going to skip. Okay, this is the stress states of concrete and the prestressing strength at the stage of prestressing. And this slide shows the behavior of prestressed battery walls on the lateral forces. In this formulation, I postulated two strength criteria. The first one is cracking of concrete, and second one is yielding or prestressing strength. And this is the first strength equation for the battery walls. This is the cracking strength. As you can see here, the cracking strength of the battery wall is the function of the amount of prestressing strength and the magnitude of prestress. This is the yield strength of battery walls. And this yield strength of the battery wall is the function of the amount of prestressing strength. Okay, this is the last part of my presentation, and so far I developed two strength equations for the prestressed battery walls, and in this part I'm going to propose two strength equations into test for verification. And for the verification, I conducted a nonlinear analysis for the prestressed battery walls. For the nonlinear analysis, I used the two-dimensional finite element analysis program that is Vector 2. The Vector 2 is developed by Professor Kyeong at the University of Toronto, and he developed a program based on the manual modified compression field theory, and this is the brief description of the modified compression field theory. And on the right, on the bottom right, you can see the analysis model of the prestressed battery walls. This is the result, and on the left, this is the lateral force and the displacement relationship. Horizontal axis is the lateral displacement of the battery wall, and the vertical axis is the lateral force acting on the battery wall. The white solid line is the results of vector 2 analysis, and the dashed line indicates the proposed strength proposed in this study. As you can see here, the proposed strength equations, the cracking strength and the yield strength are far below than the analysis results. And what is interesting here is up to the cracking point, the overall behavior is very similar to the results of vector 2 analysis. This is the results of the battery wall which was subjected to a grade of prestressed, and the same results can be found on the left figure. And on your right, you can see the basic cracking and the failure aspects of these battery walls. Okay, this is a very complicated story, so I'm going to skip. Okay, it's time to conclude my presentation. Actually, in this study, I proposed an alternative structural system for tall buildings, and through the parametric studies, I have shown that the structural performance of the proposed factory systems. And by using the compression field theory, I proposed two strength equations for the belt walls, so that by using the proposed equations, I'm expecting that we can design this kind of belt walls conservatively. And finally, I verified the proposed strength equations by using the well-known nonlinear finite element analysis methods. Thank you.
Question, comments? Okay.
Did you consider the shrinkage due to the prestressed force?
Yeah.
The
Temperature shrinkage.
Yeah. Then
Shrinkage and
the shrink you will
Shrinkage.
change the location of the column.
At temperatures, that subject is out of my research scope. At the moment, I don't have any comments about it, but that's a very good question. And actually, in order to apply this system in practice, I have to consider that issue very seriously.
One question. Okay, thank you very much. As a student and employee and worker, when I met him, he told me that I am his age. After 40 years, I wonder I will be in his position. During the last 30 years, he conducted many business projects and valuable research areas. From now, I would like to brief his, introduce his biography. If you think this brief is not enough, please go to this paper. From late 80s to early 90s, he researched about precast concrete. Through this research, it was developed Samsung Daewoo Donga large panel system. At the time, many social problems come from few of housing. Through the research, it was possible to supply so many housing. Middle 19th, he conducted two parts of research on investigation of structural stability evaluation. One is investigation of new town, including 1,255 apartments and 355 parking lot buildings. Another one is Samsung department store collapse accident. This accident was the biggest since one nation's founding. He focused of the accident with reducing column size and punching shell of the Lateral system. At the 19th, he was studying collision and non-destructive inspection in concrete structure. Through this research, he suggested a new equation of the bond strength for reinforcing bar. Early 2000s, his interesting research path was seismic performance evaluation and interpreting methods for aged apartments. Seismic design code were enacted in 1988 for building design before 1988.
They have no seismic capacity. His research was related to develop of seismic profiting technique and for aged housing. His lab was designated National Research Laboratory by Ministry of Science and Technology. At late 2000, he studied to improve performance of aged apartments, especially the research focused on improvement and structural performance and seismic performance. During the 2011, his research was concentrated in ultra highlight buildings. This research would be better to explain him directly. I am introduced to him, Professor Chung.
Thank you. Thank you. Professor Hyun and everybody who attended this seminar. And it was my great pleasure to work together with those who presented in this seminar. And now I'd like to show my recent work conducted by in super building research and development and business development center. There will be some videos which is opened by professional speakers, English speakers, who will be much better than my poor English. I put some English or Korean complementary explanations for Koreans. So please give me some videos.
Dr. Han, will you please play the movie video for that?
Today is the last day to teach in university. In last 27 years.
Super Tall Building Global R&D Center was launched with the support from Ministry of Land, Infrastructure and Transport since December of 2015 for developing super tall building core technologies for megacities that are consistently increasing. Constructing the infrastructure to support hidden champions that can create the novel growth power in the construction field and extending the global share of development technologies. In this video, 2 years of an effort to become the center will be introduced by demonstrating the establishment of Super Tall Building Center and outcome of development technologies. University is the research managing department of the Super Tall Building Center that was organized by Professor Chung and consists of approximately 25 senior researchers from the industry, universities, and institutes. Total research period is 5 years from December 2015 to December 2020, and the total R&D budget is approximately 23,600,000,000 won. And out of the total R&D budget, 20,200,000,000 won was supported by government. Super Tall Building Global R&D Center has 4 projects. The Project 1 was executed by Korea University to develop the business support type of the core technologies for super tall buildings. Project 4 was led by the Research Managing Department, TaeSung University, to develop the model for establishing the infrastructure of the global support for super tall buildings. Project 2 and Project 3 will be starting in 2018. The Project 2 will develop the overseas advancement type of core technologies for super tall buildings, and the Project 3 will develop the creative innovation type of commercialization technologies for super tall buildings. The center is located in Dankook University. Professor Chung from Dankook University is the director of the center, and the center is systematically and professionally operated with 3 vice directors, 4 committees for efficient operation, research division for development of technologies, and secretariat for overall coordination. This is the development strategies to secure the world-class global top technology and activate the center. Secure global top original technologies until year 2020. Build the infrastructure for globalization. And as a long-term goal, we have a plan to become the pioneer who can advance to the global market using the original technologies and infrastructure. This is an introduction of advanced research and field application of Project 1 that develops business support type of core technologies for super tall buildings. Development technologies consist of structural engineering and automation technologies of construction for super tall buildings. Structural engineering develops the structure and envelope design engineering technologies and active control technologies of multiple axis vibration and modes. And automation technologies of construction are lifting equipment, management technologies, and overall construction management technologies.
This
Project 1, development of design engineering technologies and generic product of irregular shaped super tall building aims for the innovative data processing technologies by integrating the traditional design engineering technologies of super tall buildings and advanced IT. Currently, optimization of shape and size of core structure and alternative generation and performance evaluation of volume as a design variable are executed on Cheongna City Tower that is preparing for new construction. Moreover, productivity of detailed design was significantly increased by developing the module that can automatically design 3D frame and rebar. Using the technologies, feasibility of construction could be inspected and precise quantity of rebar, concrete, and cast that can be calculated in real time. Those technologies were manufactured as a single platform, which is called Builder Hub. The field application and verification of the product was executed by major contractors as Daelim Construction, GS Construction, and Daewoo Construction. A pilot project with LH is also in the process of field application at the site. Next technology is about a control technology of wind vibration. Design technology of active mass damper from previous research played a big role to solve the resonance phenomenon of Technomart in Gyeong, Seoul. Currently, vibration control device is installed on the top floor of the building, and the status is monitored in real time. Furthermore, the excellence of developed technologies is recognized, and active mass damper is applied in the control tower of Incheon International Airport Terminal 2. 2 active dampers with multiple axes and modes are currently installed. Active mass damper is a domestic unique technology that is also recognized internationally. Manual control device was actively provided on global services. 2 45-ton TMD and 4 4-ton TMD will be installed on Dubai Eye, which is the world's highest Ferris wheel. Also, our technology competed against the outstanding company RWDI that installed TMD in Taipei World Financial Center and won the contract to install 150 TMD in Treasure Garden. With technology recognition from Dubai Eye, 2 33-ton tuned mass damper will be installed in New York Wheel, which is located on Staten Island, nearby Manhattan. Currently, performance of vibration control device was examined and the device is released for installation. This is a construction method of table formwork and lifting technologies. Previously, table formwork is typically operated based on the experience and dependent on manpower. Thus, the productivity of formwork was limited without a construction method model. In order to improve the productivity, algorithm that searches the optimized operation method was developed with simulation, and field-oriented and optimized table formwork could be applied. The research development team compared total operation method and and partial operation method of traditional method and algorithm on super tall building in Malaysia. As a result, 45% of operation period could be reduced. In addition, development of trolley for high-speed installation and dismantlement started. With the consultation of domestic and global professionals, required performance improvements of current table formwork was derived. Based on the deducted required performance improvements, the concept of trolley equipment developed. Trolley equipment will be a unique domestic technology and will include tilting sensor, fixing unit, hydraulic electric device, and driving motor. This technology is an automatic lifting technology for table form lifting. Problems with current listing was analyzed, and the correlation between required performance and characteristics of technology was analyzed. Consequentially, guide rail operation, table fixing method, and improvement on door opening. In order to meet all the requirements, extended door type of two-way guide rail operation process was designed and solve the problems with step pulley and table form lifting operation. Currently, prototype has been made and experimental tower test was performed. The prototype of technology will be designed and applied in the field on this October. Here are 6 major tasks of the center. The first task is establishment of the center and discovery of future specialized tasks. The center played the role as the control tower and think tank of super tall building. For securing the growth power for the future, cutting-edge research projects are consistently planned. The second task is establishment of international cooperation network tasks. Domestic hub with World Super Tall Building Association, CTBUH, was developed, and the active academic exchange with University of Notre Dame, University of Michigan, Tokyo Institute of Technology, University of Kyoto, Tsinghua University, Tongji University, and Tamgang University form consultative network groups related to small buildings. Third task is establishment of global business support system. As organization for supporting the global business, education on developed technologies will be provided and global expansion of company and pre-occupancy of global market will be actively supported. Fourth task is development of training program for fostering global workforce. In order to educate the global workforce on seismic field for super tall buildings integrated with ICT, University made the contract with small business, and a degree course supported by Small and Medium Business Administration was established to re-educate employees according to company demands in Dankook University. With the re-education, the professionals will be trained every year. Fifth task is establishment of web-based knowledge information analysis system on super tall buildings. The center established the internal and unified knowledge information analysis system on super tall buildings, and the information service with Hub will be provided through the management and advertisement of research and supervision of technologies, industry, policy, and research trend analysis. Sixth task is identification of improvement of law regime of super tall buildings. Instead of short-term review, laws related to the actual problems with super tall buildings in each phase were inspected. International operation examples are investigated to propose the mid-long-term and comprehensive law regime improvements. Establishment of super tall building center and the major task will be introduced, and several reported outcomes of developed technologies from the broadcasters and newspapers will be presented. On April of 2016, the Issue Maker magazine reported the establishment of super tall buildings in Dankook University. Super Tall Building Center will be the significant medium that proposes direction on successful Korean industry. In 10 years, this center will have foundation to be independent, and domestic companies will be the important hub that can provide the opportunity to reach out for global construction market. In order to support overseas advancement of specialized construction companies, foster super tall building specialists, and excavate energy-efficient technologies, MOU with specialized companies was executed. Also, the effort has been made to accomplish the task of the center. For application of optimized vibration control device depending on the building location and characteristics, hybrid tuned mass damper, control device with multiple access and modes, active control system was continuously developed. Currently, BIM market is dependent 100% on overseas technologies. Successful software development from venture business, Changsoft and Dankook University was reported that software is an ignition of changing paradigm of global construction technologies. On October of 2016, director of the center, Chung, received the grand prize of Seoul Construction Award from Seoul City Hall. Chung evaluated the seismic performance of his own house and super tall buildings and established the countermeasures. His contributions on increasing the safety and value of buildings were recognized, and he was the only one selected from architecture field. Outcomes of the Super Tall Building Center for the last year were briefly introduced. We will not stop here, but we will actively support and spare no effort to become the world's leading Super Tall Building Center. Our technologies make your dreams come true. Just imagine it comes true with our technologies.
Thank you for your attention. A question or comments about our Okay, anytime you can write me in our center, and I'd like to express my sincere appreciation to my colleagues who prepared this seminar, Professor Kyeong and Professor Kyeong, Professor Hyun, and Professor Dongmin, and Professor TaeSung, Professor Kyeong, and other colleagues, Dr. Chung and Dr. Hyun, and Dr. Kyeong, and the other students and colleagues. Thank you. Thank you.